Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Basics of GNSS Positioning and Receivers Technology. Our speaker today is Luca Settembre, who is working as product manager in the field of wireless connectivity and sensors for GNSS modules at Würth Elektronik eiSos. He will hold today's webinar and also answer your questions. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but are holding the webinar out of the home office. In case of technical issues or some delay, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the control panel on the right. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer your question, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. Also, you will receive the link to the presentation as well as to the recording of the webinar only in the next few weeks. And now I will hand over to our speaker, Luca, and I wish you an exciting webinar.
Thank you, Marcus, for your introduction. I am very happy for the opportunity to talk today. Today's topic is Basics of GNSS Positioning and Receivers Technology. I would like to start with today's agenda. We will start giving some fundamentals of GNSS positioning. In the second part of the presentation, I would like to present to you some of the challenges in the GNSS-based positioning. At the end of the presentation, I would like to present to you our offer of GNSS modules and show you how we can support you in building your GNSS application successfully. What is GNSS? GNSS stands for Global Navigation Satellite System and is a system providing the capabilities of position determination and time synchronization to an unlimited amount of users worldwide. The system is based on signals transmitted from a constellation of satellites. How is it possible to determine position? Based on the knowledge of distance from a sufficient number of reference points, whose position is known. Let's take an example in one dimension. In one dimension, if we know the distance from a reference point, that means that we have two possible locations for our receiver, one on the right and one on the left of our reference point. A similar situation we have in two dimensions. The locus of points with same distance from a reference point is a circle, and our location will be in one of the two intersection points between the two circles. Same situation in three dimensions where we have three spheres, and our position will be in the intersection points in one of the two intersection points of the two spheres. That means if we have a sufficient number of reference points and we are able to calculate distance from these reference points, we can calculate position. In this slide, I would like to show you how this principle is applied in GNSS. And to present to you the different segments of GNSS. We have a constellation of satellites, we have the control stations, we have the GNSS signal and the propagation segment, and the GNSS receivers on the surface of the Earth. These segments need to communicate with each other. On the basis of the previous slide, let's see how can we determine position in GNSS. We learned that we need reference points. In GNSS, the reference points are the satellites. We need to know the position of these reference points. Control stations around the Earth can predict satellite orbits, calculate their position, and send this information to the satellites. This information will be integrated in the GNSS signals transmitted by the satellites. And the second part of the GNSS signal is the ranging signal. This signal will be transmitted and will be available, will be sent to receivers. That means that the receivers will have the information about the satellite position. We can check the second point, knowledge of position of reference points. We need to be capable to calculate distances from reference points. That means calculate distances between satellite and receiver. This is done on the basis of one-way signal travel time from satellites to receiver. We will provide more details about that later in the presentation. We can check the third point. The receiver is also capable of solving a system of equations with the measurement of distance and to calculate the navigation solution, solving a system of equation. That means we are capable to calculate position out of distances. So we have all the elements we need to calculate position. In the next couple of slides, I would like to give some more details about the different segments of GNSS. I will start with the space segment, that means with the satellite navigation systems. We have 4 GNSS systems. We have the American system GPS, which is widely known. We have the European system Galileo, the Russian system GLONASS, and the Chinese system Baidu. We are talking about gigantic space programs running over decades for development and modernization. These systems provide global coverage, and every constellation has 24 to 31 satellites orbiting at around 20,000 kilometer altitude. Modern receivers support multi-GNSS. That means they can work with more than one system simultaneously. We will see later on in the presentation why and how this is, how important that is for successful positioning. Let's talk about GNSS frequency bands. We have for GNSS the frequency band between 1 and 2 gigahertz. And in this frequency slot, we have 3 different main frequency bands, which are called for GPS L1, L2, and L5, and get similar names for the other systems. We have an important slot around 1.5 gigahertz, and then the other 2 slots around 1.2 gigahertz. Signals from different constellations can coexist on the same frequency bands and can be processed correctly by the receivers. Every system offers different signals, different signal plans, different services over these frequency bands. And it is important to know that we have different access policies for the different frequency bands, for the different signals. Some of the signals will be for governmental use. Some other signals will be for commercial applications and for will be open signal available for all GNSS receivers. And these open signals are mostly spread on the frequency band L1, around 1.5 gigahertz. How can a receiver acquire a satellite signal? Each satellite is defined by a signal code which is valid only for that specific satellite. The first task for the receiver is to know this code and reproduce this code. The second step is to synchronize the code reproduced internally with the signal arriving from the satellite. Once this synchronization is done, the receiver is able to calculate distance. As already said, the measurement of distance is based on the signal travel time. So pseudorange equals signal travel time divided by speed of light, because we know that the signals travel through the atmosphere with the speed of light. And this is our first measurement of distance. Why are we calling it pseudorange? Because this measurement is affected by an error component. On the satellites, we can assume that the clock is very accurate and very, but the same assumption cannot be done for the receivers, and we need to take into account synchronization delay, and this factor which are calling here Rx delay times speed of light. The second part will be, of course, the true range, so the real distance between satellite and the receiver, and these two components will added will give us the pseudo range, so the measurement of distance that we are making. If you are tracking enough satellites, that means at least 4 satellites, we can solve this system of equations and calculate the 4 unknowns that we have. We have 3 unknowns for the user coordinates and 1 unknown for the receiver delay. That means with at least 4 equations, so 4 tracked satellite signals, we are able to determine position and to synchronize on time. Why are we also synchronizing on time? Because we are calculating an offset to a very precise satellite clock. And this is why GNSS is used not only for location, so for localization, but also for time synchronization. This concludes this first part of the presentation, where I wanted to show you how position and time are calculated in GNSS. I'll move now to the next topic, where I want to show you some challenges of GNSS-based positioning. We have in GNSS different source of errors. This can be divided into categories. The first category is propagation and instrumentation. Under this category, we have clock stability. We assumed for the satellite to have a very precise clock, but in general, we will need to correct an offset also for the satellite clocks. Why? Because just to give an idea, 1 microsecond of clock error will cause a 300-meter range error in our measurement of distance. And this will have a very strong impact on our measurement, and that means a strong impact on our accuracy. We have then orbit perturbation, which are of course hard to predict. The accuracy of the prediction of satellite orbits is also very important. And we have then also very important factor, ionospheric and tropospheric delays. This factor comes from the fact that the speed of light can slightly change through the different layers of the atmosphere, and this will impact the measurement. We have then noise and multipath effects. Second category is the satellite geometry. We can understand this through these 2 pictures on the right of this slide. In the upper picture, we have two reference points that are like far away from each other. And we have, for each reference point, the range measurement and 2 lines for the range measurement, which represent the uncertainty in the measurement. So we have 2 red lines for P1 and 2 blue lines for P2. And we know that the position of the receiver will be in this area of intersection of the measurements. Let's compare this picture with the below picture, where the 2 reference points are very close to each other. We have again the 2 lines for P1 and P2, but we see that the intersection area is in this case much bigger, and that means that our position calculation will be much more inaccurate. So we can understand that the specific satellite geometry will play an important role in determining our accuracy. Then we should ask ourselves, how can we compensate, or how can we minimize these effects? There are here, of course, different systems, different strategies. I want to mention 2 elements. The first element is that the control station around the world will not only send or predict and send satellite position, but also build models for error corrections. And one good example is the clock error. These predictions on this correction data will be sent from the control station to the satellites, and this information will be included in the GNSS signal traveling from the satellites to the receivers. Second element is satellite-based augmentation systems. These are additional systems which spread additional messages, which improve the robustness and the accuracy of the GNSS. They provide basically wide area corrections. Which application environment for our GNSS receiver? We have seen that the different countries and the different systems have populated the sky with more and more satellites over the last years. That means, in general, more satellites are available for positioning. But it's very important to understand that no matter how many satellites we have, the application environment also plays an important role. Let's take as an example this receiver inside the building. Performing positioning in this environment where all signals are blocked from the building will be very difficult, if not impossible. A second example, let's take a receiver which is now on top of this building. We understand that we have here the complete opposite situation. So this receiver has the complete view on all satellites and GNSS signals. So if this receiver supports more systems and supports multi-GNSS, means that he will have a lot of more signals available for its system of equations. That means that it will be able to select the satellites or the geometry which leads to the best spatial distribution of the satellites. We have seen that the satellite geometry plays an important role in the accuracy. So this receiver will be able to compensate that factor, choosing the best set of satellites. As third example, we consider a receiver which is between these buildings. Now, this receiver will have a limited view on the satellites. In this case, supporting multi-GNSS becomes even more important because having, for example, like a single constellation available for position could lead to the situation where we don't have enough signals to calculate position. because the equation are too less to solve the system, simply explained. That means if for this receiver supporting more systems can be maybe a nice to have feature, for this receiver will be or can be decisive for the performance. We can conclude that multi-GNSS improves the robustness to obstructed environments. In this slide, I would like to talk about some signal reception aspects which are really important when building a GNSS application. GNSS signals are extremely low in power, from minus 125 to minus 130 dBm on the Earth's surface. As we have already seen, they can be tracked because the receivers know the code transmitted by each satellite for a particular service and frequency band. We have seen that when showing how the receiver reproduces the satellite code and synchronize with it. And this is the process which takes the signal out of the level of noise. That means that the quality of the RF design, as well as choosing the right GNSS antenna solution, will be decisive for module's performance. Why? Because we need to deliver to the module the cleanest possible signal in order for the module itself to process it correctly and find reliable position solution. This concludes the second part of the presentation. In the last part of the presentation, I would like to give you some highlights about our offer of GNSS modules and of our support, and show you how we can support you in building your GNSS application. We have currently 4 GNSS modules available on the market. We have an ELARA line where we support, so with ELARA 1 and ELARA 2, where we support GPS and GLONASS. We have an Erinome line where we support GPS, Galileo, GLONASS, and Baidu, so all 4 GNSS. For each line, we have a module with integrated antenna, ELARA 1, and a module without integrated antenna. And for Erinome, line is the same. So Erinome 1 is with integrated antenna and Erinome 2 without integrated antenna. On the modules with integrated antenna, you can recognize the antenna on top of the module. These are the sizes for the 4 modules. All modules are very compact, going from the 4x4 of ELARA 2, going up to 7x7, 10x10, and 18x18 millimeters. Having an integrated antenna can save a lot of effort in the integration and matching of an external GNSS antenna. But of course, this has to be considered with all other factors, like, for example, the GNSS environment and all the considerations of the previous slide, and the specific GNSS application. Common features for these modules are the 1.5 meter position accuracy in GPS GLONASS, support of satellite-based augmentation systems, UART and I2C interfaces for communication with the external world, very fast acquisition time, the availability of low power modes, and the CE declaration for all our modules, GNSS modules. So I invite you to visit our website and have a look at the documentation for these 4 GNSS modules. Our support. We have seen how critical RF design is in relation to GNSS modules performance. So the question here is how we can help you. For each of the modules, we offer evaluation board. Evaluation board is, here is an example for a Erinome 2 module. Evaluation board is our reference design, and it's basically our recommendation for all aspects of the integration of a GNSS module on your board. For the modules without integrated antenna, so Elara 2 and Erinome 2, we give you the possibility to test two different antennas on the evaluation board. So we have a passive antenna integrated on the evaluation board and the possibility to connect an active antenna through the SMA connector. This possibility, this gives you also the possibility to get some distance from the evaluation board. For example, place your active antenna outside of the window and test from inside. That means with such a solution, with this evaluation board, you have the possibility to test these two antenna options, get a feeling of the different performance, evaluate, compare both options, and see what fits best to your application. I also highly recommend having a look at our application note GNSS antenna selection available on our website. We know that there is a wide variety of GNSS antennas available on the market, and this application note is valid support to understand which are pro and cons of the different solutions. We have compared different antennas, made some analysis, some tests, and we give you like a good report of all these tests and our recommendations in this application note. We offer a proprietary PC tool free of charge and also available on our website. This allows you to start with the module, to test the module, and also understand the software protocols. That means you can connect our evaluation board, start the software, and test the module in few simple steps, which actually I would like to show you in a live demonstration in the next slide. So I want here to give you an example of how you can start in few steps to work with our GNSS module. Let's see our setup. I'm testing with our Erinome 2 evaluation board, which is here available in my home office station. I connected the active GNSS antenna, which is included in our evaluation kit. I'm simulating the satellites with a signal generator because of data protection reasons. And I'm using our PC tool on my laptop. So we call this PC tool GNSS. Before we start with this live demonstration, I would like to shortly discuss this picture here on the right. This is a screenshot from a measurement which we made in our laboratory. And this, what you see here is the so-called 1 PPS signal. This signal is sent by the module on a corresponding pin as soon as at least 5 satellites are tracked and position is calculated with at least 5 satellites. This signal has to be used for, or is the best solution to use for timing application. That means 1 time per second, so 1 pulse per second, is sent by the module, and this signal can be used for precise timing to control external devices in your application. And every time we talk about time synchronization, the best solution is to use this signal. Okay, so I would like now to show you our PC tool within a live demonstration. So I bring the tool on the shared screen. And okay, this is our PC tool. In the below section, we see the messages coming from the module, which deliver the information about the position and the time. One added value of this tool is that you can activate this view where the messages are directly parsed by the tool, so that you can recognize the meaning of the messages, which is basically explained in every line of the messages themselves. In the upper part of the interface, we have all relevant information about position of which is determined by the model. So we have a fixed 3D condition. We are tracking 14 satellites. This is the position which is currently calculated, which is simulated in the signal generator, is the position of Olympia Tower in Munich. This is the calculated time. And I would like also to show you other views which are available in the tool. So I'll switch to the satellite view. Here we have a very good information about the satellites which are tracked by the model. So we are currently using some Galileo satellites, some GPS satellites, and some GLONASS satellites. So we are using three systems simultaneously. These are the represented like satellite position in elevation and azimuth, and also very important information delivered by this table is the signal to noise ratio. This gives you an impression of the signal quality or signal power available for the module for each satellite. Now we are in signal generator condition, and all these values are very good, are close to 40 dBHz. And this can reach with live satellites can reach 45 dBHz in very good sky conditions. And then depending on the obstructions and on the environment, they can go down to 30, 35, 25, depending on the environment and on the quality of the signal as it arrives to the model. I will switch to the configuration view. Here we have everything we need to manage the communication with the model. That means we can send the commands which are ready to use in this window. We can activate or deactivate messages. We can set a higher update rate for the model. We reach the 10 Hz update rate on the Erinome line. We can restart the module. And of course, all these messages and commands are described in our documentation, which is available on the website. And as already discussed, this tool provides a very valid support to understand better the software protocols, get familiar with that, and understand how to communicate with the model successfully. This basically concludes my presentation. I would like to thank you for your attention, and I would be very happy to answer your questions. Back to you, Marcus.
So thank you very much, Luca, for this great and interesting webinar. And as you have mentioned it, we would like to turn our attention now to your questions, and we wait a little until some questions come in. You have the opportunity to ask us the questions via the webinar control panel on the right with the chat function. So we will have a look at your question. And yeah, Luca, there is the first one. Do you have any GNSS antennas available in your portfolio?
Thank you for the question. Currently, we don't have any GNSS antenna available on the market, but this will change very soon because we'll have in the next weeks 2 new GNSS antennas available in our portfolio. So we'll have an active GNSS antenna and a passive GNSS antenna in our portfolio. And I am this will be very soon, and I highly recommend you to check our website to have a look at those solutions, which of course can work with our GNSS modules.
Okay, so then we have a look at the next question. So Luca, next question. To get the correct data at the receiver side, at least for satellite will be positioning toward the receiver, right? What is the maximum time to get correct signal in general so that we can get so that we can conclude a GPS receiver is working or not, or to check the accuracy?
As discussed during the presentation, for 4 satellites, that means 4 signals is the minimum amount to get position and time solution. You should take into account around 30 seconds to get the first valid position from the module, but this will depend on the application environment and on the for example, in the scenarios we were seen with limited view, free view, and as said, on the quality of the scenario and the quality of the signals available for the receiver.
Okay. So thank you for the explanation. And then we have a look at the next questions. If there are any questions not answered yet, we will answer them via email afterwards. So the next question is, Luca, can I change the GNSS constellation used by the module?
Thank you for the question. Yes, this is possible. In multi-GNSS modules, that means, in all our solutions, you can switch between the systems. For example, in ELARA line, you can switch between GPS GLONASS and GPS only. In the Erinome line, where you also have Galileo and Baidu, then you can set the other combinations. I can maybe add something about that. Using less constellations, of course, we have discussed that is like can be critical in obstructed environments, but the advantage is that the power consumption will be lower when less GNSS systems are used, because it also means less amount of signals has to be processed by the receiver, and so the power can be saved.
Okay. So then again, we have a look at the next question. And Luca, there we got the next one. Can I configure your GNSS module in such a way that the new position is calculated and sent out at rare intervals, for example, once per day? And
Yes, yeah, please.
yeah, and also the question is, can I use that strategy to save power?
Yes, this is actually the perfect strategy to save power in situations or in applications where only the new position is needed only at rare intervals. So the modules have 2 main power modes: one sleep mode that we can call hibernate, and one full power mode where like the module looks for available signals and tries to calculate position. So the idea behind low power modes in our modules is always to alternate between these two modes, like the full power mode where we have current consumption around, for example, 50 milliampere, and the low power mode where we have current consumption in the range of microampere. So we can, with a simple command, we can configure a schedule between low power mode, or hibernate, and full power. And we can easily build our schedule that, for example, gets our, set our module in such a way that only once per day wakes up, calculate the new position, sends it out through the available interface on the used interface, and then goes back to sleep. And of course, this will save. This can be used to save power, of course.
Okay. Then we got the next question. Can we use linear polarized antenna for GPS receiver? And what is NMEA packets?
Yes, this is possible. And what are NMEA packets? NMEA is a communication protocol which is widely used in GNSS receivers, and it's actually the protocol that I was using during the live demonstration with the software tool. So the NMEA is a standard defining the content of the messages, or the content of the messages coming from the GNSS module, so that we are able to interpret these messages, to parse these messages, and get the information we need out of them.
Okay, thank you for the explanation. And then we have another look at the next questions. So the next question, are there plans for GNSS modules for precision timing applications for like a high PPS stability and timing accuracy like 15 nanoseconds?
Thank you for the question. We don't have a concrete plan about yet this point. Of course, these four modules are our. I think these four modules are a good basis, like a good offer at this point for the for GNSS. But of course, we know that there are other possibilities. We look at the market like continuously, and we will work on finding the best products. I unfortunately cannot be more concrete than that at this point.
Okay. So we have the next look for the next question. And we also have the next question. Does GPS or also GNSS signal depends on weather?
GNSS signals are not affected by weather condition. There was some research about that, but basically there's no effect we can see on the GNSS signals coming from the weather conditions. Of course, other kind of situation is if our module is sunk in ice, or a high layer of ice is on that, or snow, that of course can have an impact on the signals coming from the satellites, and it means on our accuracy.
Okay, then we have time for another question, and we have a look for it. Yeah, look at that. We got the last question. Is indoor positioning not possible at all with GNSS modules, or is it possible with limited performance?
All right, this is a complex or a critical topic in GNSS. We know we all know the experience of driving on the highway and then driving into a tunnel, and then our navigation systems doesn't show our position anymore, just show signal is lost, GPS signal is lost. So that shows us that we cannot, basically, it's very critical, it's very hard to work with GNSS in scenarios where GNSS signals are blocked from obstructions, or what we call GNSS denied environments. The situation can be, of course, can be different if the layers of obstructions are smaller, are thinner. Of course, if I now use my GNSS antenna indoor, but that lies on my window, like with only one layer obstructing the signal, and then if I use, for example, an active antenna, this of course can change the situation, and I could get I could get my GNSS modules to work indoor. But again, the line of sight and the free view to the satellites or to this is decisive for good performance of GNSS.
Okay, so thank you, Luca, for the answers. And now we are finished with our webinar. If there are any questions open or left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our webinar. So, and also many thanks to you, Luca, for this really great webinar.
Thank you, Marcus. Thank you to all our listeners, and have a great rest of the day.
Also from me, have a good day and goodbye.